Hello everyone, welcome to my lecture. Becoming a unicorn. Data science is very popular term these days and it gets applied to so many things that its meanings has become very vague. So I would like to start this lecture by giving you the definition that I use. I have found that this one gets right to the heart of what sets it apart from other disciplines. Here goes. Data science means doing analytics work that, for one reason or another, requires a substantial amount of software engineering skills. Sometimes the final deliverable is the kind of thing a statistical or business analyst might provide, but achieving that goal demands software skills that your typical analyst simply doesn't have. For example, a dataset might be so large that you need to use distributed computing to analyze it, or so convoluted in its format that many lines of code are required to parse it. In many cases, data scientists also have to write big chunks of production software that implement their analytics ideas in real time. In practice, there are usually other differences as well. For example, data scientists usually have to extract features from raw data, which means that they tackle very open-ended problems, such as how to quantify the spamminess of an email. It's very hard to find people who can construct good statistical models, hack quality software, and relate this all in a meaningful way to business problems. It's a lot of hats to wear. These individuals are so rare that recruiters often call them unicorns. The message of this lecture is that it is not only possible but also relatively straightforward to become a unicorn. It's just a question of acquiring the particular balance of skills required. Very few educational programs take all teach all of these skills, which is why unicorns are rare. But that's mostly a historical accident. It is perfectly reasonable for a single person to have the whole palette of abilities, provided they are willing to ignore the traditional boundaries between different disciplines. This lecture aims to teach you everything you will need to know to be a competent data scientist. My guess is that you are either a computer programmer looking to learn about analytics or more of a mathematician trying to bone up on their coding. You might also be a business person who needs the technical skills to answer your business question, or simply an interested layman. Whoever you are, though, this lecture will teach you the concepts you need. This lecture is not comprehensive. Data science is too big an area for any person to cover all of it. Besides, the field is changing so fast that any comprehensive lecture would be out of date before it came off the presses. Instead, I have aimed for two goals. First, I want to give a solid grounding in the big picture of what data science is, how to go about doing it, and the foundational concepts that will stand the test of time. Second, I want to give a complete skill set, in the sense that you have the nuts and bolts knowledge to go out and do data science work. You can code in Python, you know the libraries to use, most of the big machine learning models, etc. Even if particular projects or companies might require that you pick up a new skill set from somewhere else. Aren't data scientists just overpaid statisticians? Nate Silver, a statistician famous for accurate forecasting of US elections, once famously said, "I think data scientist is a sexed up term for statistician." He has a point, but what he said is only partly true. The discipline of statistics deals mostly with rigorous mathematical methods for solving well-defined problems. Data scientists spend most of their time getting data into a form where statistical methods could even be applied. This involves making sure that the analytics problem is a good match to business objectives, extracting meaningful features from the raw data and coping with any pathologies of the data or weird edge cases. Thank you. Hello everyone, welcome to my lecture, Becoming a Unicorn. Data science is a very popular term these days, and it gets applied to so many things that its meanings has become very vague. So I would like to start this lecture by giving you the definition that I use. I have found that this one gets right to the heart of what sets it apart from other disciplines. Here goes. Data science means doing analytics work that, for one reason or another, requires a substantial amount of software engineering skills. Sometimes the final deliverable is the kind of thing a statistician or business analyst might provide, but achieving that goal demands software skills that your typical analyst simply doesn't have. For example, a dataset might be so large that you need to use distributed computing to analyze it, or so convoluted in its format that many lines of code are required to parse it. In many cases, data scientists also have to write big chunks of production software that implement their analytics ideas in real time. In practice, there are usually other differences as well. For example, data scientists usually have to extract features from raw data, which means that they tackle very open-ended problems such as how to quantify the spamminess of an email. Aren't data scientists just overpaid statisticians? Nate Silver, a statistician famous for accurate forecasting of US elections, once famously said, "I think data scientist is a sexed up term for a statistician." He has a point, but what he said is only partly true. The discipline of statistics deals mostly with rigorous mathematical methods for solving well-defined problems. Data scientists spend most of their time getting data into a form where statistical methods could even be applied. This involves making sure that the analytics problem is a good match to business objectives, extracting meaningful features from the raw data, and coping with any pathologies of the data or weird edge cases. Once that heavy lifting is done, you can apply statistical tools to get the final result, although in practice you often don't even need them. Professional statisticians need to do a certain amount of pre-processing themselves, but there is a massive difference in degree. Historically, data science emerged as a field independently from statistics. Most of the first data scientists were computer programmers or machine learning experts who were working on big data problems. They were analyzing datasets of the kind that statisticians don't touch: HTML pages, image files, emails, raw output, logs of web servers, and so on. These datasets don't fit the mold of relational database or statistical tools. So for decades, they were just piling up without being analyzed. Data science came into being as a way to finally milk them for insights. Why is it all in Python anyway? The example code in this lecture is all in Python, except for a few domain specific languages such as SQL. My goal isn't to push you to use Python. There are lots of good tools out there, and you can use whichever ones you want. However, I want to use one language for all of my examples. This keeps the lecture readable, and it also lets reader follow the whole lecture while only knowing one language. Of the various languages available, there are two reasons why I choose Python. Number 1. Python is the most popular language for data scientists. R is its only major competitor, at least when it comes to free tools. I have used both extensively and I think that Python is flat out better. Number 2. I like to say that for any task, Python is the second best language. It's a jack of all trades. If you only need to worry about statistics or numerical computation or web parsing, then there are better options out there. But if you need to do all of these things within a single project, then Python is your best option. Since data science is so inherently multidisciplinary, this makes it a perfect fit. Example code and datasets. This lecture is rich in example code in fairly long chunks. This was done for two reasons. Number 1, as a data scientist, you need to be able to read longest piece of codes. This is a non-optional skill, and if you aren't used it, then this will give you a chance to practice. Number 2, I wanted to make it easier for you to poach the code from this lecture if you feel so inclined. Thank you. Hello everyone, welcome to my lecture, Becoming a Unicorn. Data science is very popular term these days, and it gets applied to so many things that its meanings has become very vague. So I would like to start this lecture by giving you the definition that I use. I have found that this one gets right to the heart of what sets it apart from other disciplines. Here goes. Data science means doing analytics work that, for one reason or another, requires a substantial amount of software engineering skills. Sometimes the final deliverable is the kind of thing a statistical or business analyst might provide, but achieving that goal demands software skills that your typical analyst simply doesn't have. For example, a dataset might be so large that you need to use distributed computing to analyze it, or so convoluted in its format that many lines of code are required to parse it. In many cases, data scientists also have to write big chunks of production software that implement their analytics ideas in real time. In practice, there are usually other differences as well. For example, data scientists usually have to extract features from raw data, which means that they tackle very open-ended problems, such as how to quantify the spamminess of an email. It's very hard to find people who can construct good statistical models, hack quality software, and relate this all in a meaningful way to business problems. It's a lot of hats to wear. These individuals are so rare that recruiters often call them unicorns. The message of this lecture is that it is not only possible but also relatively straightforward to become a unicorn. It's just a question of acquiring the particular balance of skills required. Very few educational programs teach all of these skills, which is why unicorns are rare. But that's mostly a historical accident. It is perfectly reasonable for a single person to have the whole palette of abilities, provided they are willing to ignore the traditional boundaries between different disciplines. This lecture aims to teach you everything you will need to know to be a competent data scientist. My guess is that you are either a computer programmer looking to learn about analytics, or more of a mathematician trying to bone up on their coding. You might also be a business person who needs the technical skills to answer your business question, or simply an interested layman. Whoever you are, though, this lecture will teach you the concepts you need. This lecture is not comprehensive. Data science is too big an area for any person to cover all of it. Besides, The field is changing so fast that any comprehensive lecture would be out of date before it came off the presses. Instead, I have aimed for two goals. First, I want to give a solid grounding in the big picture of what data science is, how to go about doing it, and the foundational concepts that will stand the test of time. Second, I want to give a complete skill set in the sense that you have the nuts and bolts knowledge to go out and do data science work. You can code in Python, you know the libraries to use, most of the big machine learning models, etc. Even if particular projects or companies might require that you pick up a new skill set from somewhere else. Aren't data scientists just overpaid statisticians? Nate Silver, a statistician famous for accurate forecasting of US elections, once famously said, I think data scientist is a sexed up term for statistician. He has a point, but what he said is only partly true. The discipline of statistics deals mostly with rigorous mathematical methods for solving well-defined problems. Data scientists spend most of their time getting data into a form where statistical methods could even be applied. This involves making sure that the analytics problem is a good match to business objectives, extracting meaningful features from the raw data and coping with any pathologies of the data or weird edge cases. Thank you. Hello everyone, welcome to my lecture. Programming languages. One of the most obvious things that separate data scientists from traditional business analysts and statisticians is that they spend a lot of their time writing code in a more or less normal programming language as software engineers do. Sometimes it's a statistically oriented language such as R, but even that is a far cry from something such as Excel or a graphical package such as Tableau. This lecture will discuss why that is and give a brief survey of some of the more popular languages. It will then dive into the weeds of Python, my personal language of choice and the most popular option among data scientists. If you already know Python and its technical libraries, then feel free to skim. If not, then this lecture will give you the foundation in Python to understand the example code in the rest of the lecture. Hello everyone, welcome to my lecture, a survey of programming languages for data science. There are many programming language options available for data scientists. This section will give you a rundown of some of the most popular ones. Python. The example code in this lecture is generally in Python for a number of reasons. In my opinion, it is the best programming language available for general purpose use, but that's largely a matter of personal taste. It is also a very popular choice among data scientists who feel like it balances the flexibility of a conventional scripting language with the numerical muscles of a good mathematics package. Python was developed by Guido van Rossum and first released in 1991. The language itself is a high-level scripting language with functionality similar to Perl and Ruby and with an unusual clean and self-consistent syntax. Outside of the core language, Python has several open-source technical computing libraries that make it a powerful tool for analytics. R. Aside from Python, R is probably the most popular programming language among data scientists. Python is a scripting language designed for computer programmers, which has been augmented with libraries for technical computing. In contrast, R was designed by and for statisticians, and it is natively integrated with graphics capabilities and extensive statistical functions. It is based on S, which was developed at Bell Labs in 1976. R was brilliant for its time and a huge step up from the Fortran routines that it was competing with. In fact, many of Python's technical computing libraries are just ripping off the good ideas in R. But almost 40 years later, R is showing its age. Specifically, there are areas where the syntax is very clunky. The support for strings is terrible and the type system is antiquated. In my mind, the main reason to use R is just that there are so many special libraries that have been written for it over the years, and Python has not covered all the little special use case yet. I no longer use R for my own work, but it is a major force in the data science community and will continue to be for the foreseeable future. In the statistics community, R is still the lingua franca. You should know about it even if you don't use it yourself. MATLAB and Octave. The data science community skews strongly toward open source software, so good proprietary programs such as MATLAB often get less credit than they deserve. Developed and sold by the MathWorks Corporation, MATLAB is an excellent package for numerical computing. It has a more consistent syntax compared to R and more numerical muscle compared to Python. A lot of people coming from physics or mechanical/electrical engineering backgrounds are well versed in MATLAB. It is not as well suited to large software frameworks or string-based data modeling, but it is best in class for numerical computing. If you like MATLAB syntax but don't like paying for software, then you could also consider Octave. It is an open source version of MATLAB. It doesn't capture all of MATLAB's functionality and certainly doesn't have the same support infrastructure, but it's a fine option. SAS. SAS is a proprietary statistics framework that dates back to the 1960s. Similar to R, there is a tremendous amount of entrenched legacy code written in SAS and a wide range of functionality that has been put into it. However, the language itself is very aligned to somebody more used to modern language. SAS can be great for the business statistics application that is so popular in, but I don't recommend it for general purpose data science. Scala. Scala is an up and coming language that shows a lot of promise. It is not currently a suitable general purpose tool for data scientists because it doesn't have the library support for analytics and visualizations. However, that could easily change in the same way that it did with Python. Scala is similar to Java under the hood, but has a much similar syntax with a lot of powerful features borrowed from other languages. It works both for general purpose scripting and for large scale production software. Many of the most popular big data technologies are written in Scala. Thank you. Hello everyone, welcome to my lecture, Python Crash Course. This section will give you a quick tutorial on the Python language. My goal is to get you up and running quickly with the basics of the language, especially so that you can understand the example code in the lecture. The tutorial is far from exhaustive. There are many aspects of Python that I don't discuss, and in particular, I ignore most of its many built-in libraries. Some of this material will be covered later in the lecture when it becomes relevant. The next section will give you an introduction to Python technical libraries, which elevate it from a solid scripting language to a one-stop shop for data science. A note on versions. There are a number of versions of the Python language out there. As of this writing, the Python 2.7 series was by far the most popular for data scientists. The main reason for this is that all of the numerical computing libraries work with it. In 2008, Python 3.0 was released, and it broke backward compatibility with Python 2.7. This was a big deal because the Python community tends to be very careful about keeping things mutually consistent. Hello World script. A common way to learn a new programming language is to first write a Hello World program. This is a program that just prints the text Hello World to the screen. If you can write it and run it, then you know you have your software environment set up correctly and you know how to use it. After that point, you are ready to roll with the series code. There are two ways you can run Python code, and I will walk you through Hello World in both of them. Either you can open up the Python interpreter and enter your commands one at a time, which is very useful for exploring data and experimenting with that you want to do, or you can put your code into a file and run it at once. To run code in the interpreter on a Mac or Linux system, do the following. Number 1. Go to the command terminal. 2. Type Python and press enter. This will display the command prompt. Type 3. Type print hello world and press enter. The phrase hello world should print on the screen. 4. The whole thing should appear as follows. 5. Congratulations, you have just run a line of Python code. 6. Press Ctrl D to close the interpreter. The process is very similar if you are working in a Windows environment. In place of the command terminal, you are likely to use PowerShell. It is the Windows equivalent of a bash terminal. For editing your source code, Visual Studio is a powerful IDE that is ubiquitous among Windows programmers. Python's technical libraries. Python was designed mostly as a tool for software engineers, but there is an excellent suite for libraries available that make it a first-class environment for technical computing, competing with the likes of MATLAB and R. The main ones which will be covered in this lecture are as follows. Pandas. This is the big one for you to know. It stores and operates on data in data frames very efficiently and with a sleek, intuitive API. NumPy. This is a library for dealing with numerical arrays in ways that are fast and memory efficient, but it's clunky and low level for a user. Under the hood, Pandas operates on NumPy arrays. skitlearn. This is the main machine learning library and it operates on NumPy arrays. You can take Pandas objects, turn them into NumPy arrays, and then plug them into skitlearn. Matplotlib. This is the big plotting and visualization library similar to NumPy. It is a low level and a bit clunky to use directly. Pandas provides human friendly wrappers that call MATLAB routines. SciPy. This provides a suite of functions that perform fancy numerical operations on NumPy arrays. These aren't the only technical computing libraries available in Python, but they are by far the most popular, and together they form a cohesive, powerful tool suite. NumPy is the most fundamental library. It defines the core numerical arrays that everything else operates on. However, most of your actual code, especially data mounting and feature extraction, will be working within pandas, only switching to the other libraries as needed. The rest of this lecture will be a quick crash course on the basic data structure of pandas. Thank you. Hello everyone, welcome to my lecture. Supervised versus unsupervised. There are two main types of machine learning called supervised and unsupervised. In supervised learning, your training data consists of some points and a level or target value associated with them. The goal of the algorithms is to figure out some way to estimate that target value. For example, we might have data on several medical patients saying what was in a drop of their blood and then whether they were later found to have cancer. If we want to use blood samples from future patients to assess their cancer risk, this is a supervised learning problem. In unsupervised learning, there is just raw data without any particular thing that is supposed to be predicted. Unsupervised algorithms are used for finding patterns in the data in general, teasing apart its underlying structure. Clustering algorithms, which try to break a dataset down into natural clusters, are a prototypical example of unsupervised learning. Supervised learning is somewhat more common in real applications. Business situations usually dictate a specific thing that you are trying to predict rather than a broad see what there is to see approach. However, unsupervised learning algorithms are often used as a pre-processing step for extracting meaningful features from a data point, with whose features ultimately getting used for supervised learning. Training data, testing data, and the great boogeyman of overfitting. By far the greatest headache in machine learning is the problem of overfitting. This means that your results do great for the data you trained them on, but they don't generalize to other data in the future. As an extreme case, imagine that your dataset of medical patients included their names and your trained classifier just remembered the names of everybody who had cancer and made prediction based on that. It would give perfect prediction for everybody it was trained on, but would be useless for assessing anybody else's cancer risk. The solution is to train on some of your data and assess performance on other data. This can be done in a number of ways. Most basically, you randomly divide your data points between training and testing. Randomness is critically important so as to avoid unintentional sources of bias. Honestly, this crudely simple approach is often good enough in practice. A fancier method that works specifically for supervised learning is called k-fold cross-validation. The goal here isn't to measure the performance of a particular fitted classifier, but rather a family of classifiers. Cross-validation is done this way. Divide the data randomly into k partitions. Train a classifier on all but one partition and test its performance on the partition that was left out. Repeat, but choosing a different partition to leave out and test on continue for all the partitions so that you have k different trained classifiers and k performance metrics for them. Take the average of all the metrics. This is the best estimate of the true performance of this family of classifiers when it is trained on this kind of data. If you are being very rigorous about your statistics, it is common to divide your data into a training set, a testing set, and a validation set. You only get to examine the validation set at the very end to test hypothesis and the performance of your model. This is done to avoid a very subtle form of statistical bias. I don't know a name for it, but there is another approach I have used that is great in many real applications. Oftentimes, there's a situation where a model is retrained periodically, say every week, incorporating the new data acquired in the previous week. In these cases, it makes sense to train on all the data for week end and the previous weeks and then test it all the data for week n plus 1. The reasons why people click on ads might have changed a little bit over the course of the week, making the model slightly outdated. So testing on data from the same time period can artificially inflate your performance. Thank you. Hello everyone, welcome to my lecture, Machine Learning Overview. In my mind, machine learning is technically a subset of statistics. However, that's not how it might look from the outside. For historical reasons, machine learning has evolved largely independently from statistics, in some cases reinventing the same techniques and giving them a different name, and in other cases inventing whole new ideas without statisticians supposedly involved. Classical statistics grew largely out of the needs of governments in processing census data and the agriculture industry. Machine learning evolved later and largely as an outgrowth of computer science. Early computer scientists, in turn, were drawn from the ranks of physicists and engineers. So the DNA is quite different and the tools have diverged a lot, but ultimately they are tackling the same problems. Machine learning has become a catch-all term that covers a lot of different areas, ranging from classification to clustering. As such, I can't really give you a crisp definition of what it means. However, there are several commonalities that pretty much all machine learning algorithms seem to work with. It's all done using computers, leveraging them to do calculations that would be interactable by hand. It takes data as input. If you are simulating a system based on some idealized model, then you aren't doing machine learning. The data points are thought of as being samples from some underlying real-world probability distribution. The data is tabular. There is one row per data point and one column per feature. The features are all numerical, binary or categorical. Historical context. Machine learning was partly born out of the initial failures of the artificial intelligence movement. For a long time, people were very focused on the idea that computers could be made to think, and it was widely expected that thinking machines were only a few years away. There is an anecdote that Marvin Minsky, one of the founders of artificial intelligence, once assigned a grad student the task of working out computer vision over the course of a summer. People were thinking about the human brain as a big logic engine, and a lot of the focus was on getting computers to mimic the logical processing that humans do. AI failed, and it's partly out of embarrassment on behalf of their discipline that the term artificial intelligence is rarely used in computer science circles. We are as far away from mimicking human intelligence as we have ever been, partly because the human brain is fantastically more complicated than a mere logic engine. The focus has shifted away from creating true intelligence and toward using computers to do tasks that historically a human has to do. This includes things such as recognizing whether there is a bird in a photograph, telling whether an email is spam, or identifying that an interesting event has occurred in a time series. Machine learning was built up on using computers as proxies for human judgment in specific, limited situations. Of course, the techniques thus developed can be applied to many areas, even ones where human judgment is never applied in practice. So machine learning has matured into a standard toolset for any data scientist. The kinds of tools being used shifted as well. Artificial intelligence traditionally took a rule-based approach that used logical interference to reach conclusions. Machine learning is much more probabilistic in the way it makes models and inferences. As a final note, some people might criticize this lecture for not going into nearly enough depth, especially with regard to cutting edge developments in areas such as deep learning. The reasons for this is simple. In my experience, data scientists rarely get the far into the weeds. Machine learning experts spend a lot of time improving their classifiers with all the latest tricks, but data scientists tend to use of these self classifiers, instead pouring their effort into finding good features to plug into them. Thank you. Hello everyone, welcome to my lecture. Supervised versus unsupervised. There are two main types of machine learning called supervised and unsupervised. In supervised learning, your training data consists of some points and a level or target value associated with them. The goal of the algorithms is to figure out some way to estimate that target value. For example, we might have data on several medical patients saying what was in a drop of their blood and then whether they were later found to have cancer. If we want to use blood samples from future patients to assess their cancer risk, this is a supervised learning problem. In unsupervised learning, there is just raw data without any particular thing that is supposed to be predicted. Unsupervised algorithms are used for finding patterns in the data in general, teasing apart its underlying structure. Clustering algorithms, which try to break a dataset down into natural clusters, are a prototypical example of unsupervised learning. Supervised learning is somewhat more common in real applications. Business situations usually dictate a specific thing that you are trying to predict rather than a broad see what there is to see approach. However, unsupervised learning algorithms are often used as a pre-processing step for extracting meaningful features from a data point, with whose features ultimately getting used for supervised learning. Training data, testing data, and the great boogeyman of overfitting. By far the greatest headache in machine learning is the problem of overfitting. This means that your results do great for the data you trained them on, but they don't generalize to other data in the future. As an extreme case, imagine that your dataset of medical patients included their names and your trained classifier just remembered the names of everybody who had cancer and made prediction based on that. It would give perfect prediction for everybody it was trained on, but would be useless for assessing anybody else's cancer risk. The solution is to train on some of your data and assess performance on other data. This can be done in a number of ways. Most basically, you randomly divide your data points between training and testing. Randomness is critically important so as to avoid unintentional sources of bias. Honestly, this crudely simple approach is often good enough in practice. A fancier method that works specifically for supervised learning is called k-fold cross-validation. The goal here isn't to measure the performance of a particular fitted classifier, but rather a family of classifiers. Cross-validation is done this way. Divide the data randomly into k partitions. Train a classifier on all but one partition and test its performance on the partition that was left out. repeat, but choosing a different partition to leave out and test on continue for all the partitions, so that you have get different trained classifiers and key performance metrics for them. Take the average of all the metrics. This is the best estimate of the true performance of this family of classifiers when it is trained on this kind of data. If you are being very rigorous about your statistics, it is common to divide your data into a training set, a testing set, and a validation set. You only get to examine the validation set at the very end to your test hypothesis and the performance of your model. This is done to avoid a very subtle form of statistical bias. I don't know a name for it, but there is another approach I have used that is great in many real applications. Oftentimes there's a situation where a model is retrained periodically, say every week, incorporating the new data acquired in the previous week. In these cases, it makes sense to train on all the data for week end and the previous weeks and then test it all the data for week n plus 1. The reasons why people click on ads might have changed a little bit over the course of the week, making the model slightly outdated. So testing on data from the same time period can artificially inflate your performance. Thank you. Hello everyone, welcome to my lecture. Data munging, string manipulation, regular expressions, and data cleaning. This lecture is about some of the pathologies that you will see in real world data. It takes about some of the most common ones, where they come from and how they can be addressed. Data pathologies come in roughly two types. The first are formatting issues. This includes inconsistent capitalization, extraneous white space, and things of that nature. Often these are straightforward to solve with appropriate pre-processing of the data. The second category involves the actual content of the data. Duplicate entries, major outliers, and null values are all examples. It often requires some detective work to figure out what these issues mean in a particular situation and hence how they should be addressed. My goals in this lecture are twofold. Firstly, I want to give you an appreciation for the breadth of issues that can be present in real world data and equip you to quickly identify and diagnose problems. Secondly, I want to teach you tools that can be used to solve the problems. Specifically, I will discuss various types of string manipulation. Manipulating strings of text might seem boring at first glance, but it's one of the most powerful tools a data scientist can have. I would put it on par with machine learning itself. String manipulation can be used to address any data formatting problems, and in many cases, it is the only suitable solution. But it is also invaluable for creating scripts to pull information out of raw data. Sometimes when you encounter a new dataset, there is a right way to process it, which requires learning a new organizational paradigm and complicated tools that implemented it. Alternatively, the quick and dirty way is to spend an hour hacking together a script that pulls out the specific data you need. You can guess which of these approaches is often more expedient if you need the preliminary result by tomorrow. The worst dataset in the world. The worst industrial dataset that I ever worked with was the first one. It was a collection of server logs describing queries that had been received by a large collection of servers that my client owned. A given server could be referred to by a number of different names. Most lines of the logs were gobbledygook that were useless to me. Some of the key fields were encoded in weird hexadecimal. There were no rows or columns. Instead, Each line had its own structure. It was awful. Then I worked with my second industrial dataset and discovered that they are all like that. Your worst dataset will probably be your first one too. Whenever there is a large organization, a complicated data collection process, or several datasets that have been merged, issues tend to pile up. They are rarely documented and often only come to light when some poor data scientist is tasked with analyzing them. You have been warned. How to identify pathologies. One of the most embarrassing things that can happen in data science is to have to retract results that you have presented because you realize that you processed the data incorrectly. Given how convoluted datasets often are, you should have a healthy degree of paranoia about this happening. To identify these issues early, I have 4 pieces of advice. If the data is text, look directly at the raw file rather than just reading it into your script. 2. Read supporting documentation if it's available. Often the data is hard to understand because it uses strange codes or conventions whose meaning is documented in some accompanying PDF files or something. 3. Have a battery of standard diagnostic questions you ask about the data. Does this column contain nulls? Are all the identifiers in table A present in table B and vice versa? Things like that. 4. Do sanity checks, where you use the data to derive things that you already know. If you count the customers in the dataset and it isn't equal to the number of customers you know the company has, then chances are you weren't identifying unique customer correctly. Thank you. Hello everyone, welcome to my lecture. Data munging, string manipulation, regular expressions, and data cleaning. Data pathologies come in roughly 2 types. The first are formatting issues. This includes consistent capitalization, extraneous white space, and things of that nature. The second category involves the actual content of the data. Duplicate entries, major outliers, and null values are all examples. My goal in this lecture are twofold. Firstly, I want to give you an appreciation for the breadth of issues that can be present in real-world data and equip you to quickly identify and diagnose problems. Second, I want to teach you tools that can be used to solve the problems. Specifically, I will discuss various types of string manipulation. Problems with data content. Duplicate entries. You should always check for duplicate entries in a dataset. Sometimes you are important in some real world way. In those cases, you usually want to condense them into one entry, adding an additional column that indicates how many unique entries there were. Multiple entries for a single entity. This case is a little more interesting than duplicate entries. Often, each real-world entity logically corresponds to one row in the dataset, but some entities are repeated multiple times with different data. The most common causes of this is that some of the entries are out of date and only one row is currently correct. Missing entries. Most of the time, when some entities are not described in a dataset, they have some common characteristics that kept them out. For example, let's say that there is a log of all transactions from the past year. We group the transaction by customer and add up the size of the transaction for each customer. This dataset will have only one row per customer, but any customer who had no transaction in the past year will be left out entirely. In a case such as this, you can join the derived data up against some known set of all customers and fill in the appropriate values for the ones who were missing. Nulls. Null entries typically mean that we don't know a particular piece of information about some entity. The question is why. Most simply, nulls can arise because the data collection process was botched in some way. What is this means depends on the context. When it comes into to do analytics, nulls cannot be processed by many algorithms. In these cases, it is often necessary to replace the missing values with some reasonable proxy. What you will see most often is that it is guessed from other data fields, where you simply plug in the mean of all the non-null values. Huge outliers. Sometimes a massive outlier in the data is there because there was truly an aberrant event. How to deal with that depends on the context. Sometimes the outliers should be filtered out of the dataset. In web traffic, for example, you are usually interested in predicting pages views by humans. A huge spike in recorded traffic is likely to come from a bot attack rather than any activities of humans. Formatting issues. Formatting is irregular between different tables/columns. This happens a lot, typically because of how the data was stored in the first place. It is an especially big issue when joinable/groupable key are irregularly formatted between different datasets. Extra white space. For such a small issue, it is almost comical how often random white space confounds analysis when people try to say join the identifier ABC against ABC for two different datasets. White space is especially insidious because when you print the data to the screen to examine it, the white space might be impossible to discern. Irregular capitalization. Python strings have lower and upper methods which will return a copy of the original string with all letters set to uppercase or lowercase. Inconsistent delimiters. Usually a dataset will have a single delimiter, but sometimes different tables will use different ones. Irregular null format. There are a number of different ways that missing entries are encoded into CSV files, and they should all be interpreted as nulls when the data is read in. Invalid character. Some data files will randomly have invalid bytes in the middle of them. Some programs will throw an error if you try to open up anything that isn't valid text. In these cases, you may have to filter out the invalid bytes. Operating system incompatibilities. Different operating systems have different file conventions, and sometimes that is a problem when opening a file that was generated one OS on a computer that runs a different one. Wrong software versions. Sometimes you will have a file of a format that is designed to be handled by a specific software package. However, when you try to open it, a very mystifying error is thrown. This happens, for example, with data compression formats. Thank you. Hello everyone, welcome to my lecture. Data munging, string manipulation, regular expressions, and data cleaning. This lecture is about some of the pathologies that you will see in real world data. It takes about some of the most common ones, where they come from and how they can be addressed. Data pathologies come in roughly two types. The first are formatting issues. This includes inconsistent capitalization, extraneous white space, and things of that nature. Often these are straightforward to solve with appropriate pre-processing of the data. The second category involves the actual content of the data. Duplicate entries, major outliers, and null values are all examples. It often requires some detective work to figure out what these issues mean in a particular situation and hence how they should be addressed. My goals in this lecture are twofold. Firstly, I want to give you an appreciation for the breadth of issues that can be present in real world data and equip you to quickly identify and diagnose problems. Secondly, I want to teach you tools that can be used to solve the problems. Specifically, I will discuss various types of string manipulation. Manipulating strings of text might seem boring at first glance, but it's one of the most powerful tools a data scientist can have. I would put it on par with machine learning itself. String manipulation can be used to address any data formatting problems, and in many cases it is the only suitable solution. But it is also invaluable for creating scripts to pull information out of raw data. Sometimes when you encounter a new dataset, there is a right way to process it, which requires learning a new organizational paradigm and complicated tools that implemented it. Alternatively, the quick and dirty way is to spend an hour hacking together a script that pulls out the specific data you need. You can guess which of these approaches is often more expedient if you need the preliminary result by tomorrow. The worst dataset in the world. The worst industrial dataset that I ever worked with was the first one. It was a collection of server logs describing queries that had been received by a large collection of servers that my client owned. A given server could be referred to by a number of different names. Most lines of the logs were gobbledygook that were useless to me. Some of the key fields were encoded in weird hexadecimal. There were no rows or columns. Instead, each line had its own structure. It was awful. Then I worked with my second industrial dataset and discovered that they are all like that. Your worst dataset will probably be your first one too. Whenever there is a large organization, a complicated data collection process, or several datasets that have been merged, issues tend to pile up. They are rarely documented and often only come to light when some poor data scientist is tasked with analyzing them. You have been warned. How to identify pathologies. One of the most embarrassing things that can happen in data science is to have to retract results that you have presented because you realize that you processed the data incorrectly. Given how convoluted datasets often are, you should have a healthy degree of paranoia about this happening. To identify these issues early, I have 4 pieces of advice. If the data is text, look directly at the raw file rather than just reading it into your script. 2. Read supporting documentation if it's available. Often the data is hard to understand because it uses strange codes or conventions whose meaning is documented in some accompanying PDF files or something. 3. Have a battery of standard diagnostic questions you ask about the data. Does this column contain nulls? Are all the identifiers in table A present in table B and vice versa? Things like that. 4. Do sanity checks, where you use the data to derive things that you already know. If you count the customers in the dataset and it isn't equal to the number of customers you know the company has, then chances are you weren't identifying unique customer correctly. Thank you. Hello everyone, welcome to my lecture. Data munging, string manipulation, regular expressions, and data cleaning. Data pathologies come in roughly 2 types. The first are formatting issues. This includes consistent capitalization, extraneous white space, and things of that nature. The second category involves the actual content of the data. Duplicate entries, major outliers, and null values are all examples. My goal in this lecture are twofold. Firstly, I want to give you an appreciation for the breadth of issues that can be present in real-world data and equip you to quickly identify and diagnose problems. Second, I want to teach you tools that can be used to solve the problems. Specifically, I will discuss various types of string manipulation. Problems with data content. Duplicate entries. You should always check for duplicate entries in a dataset. Sometimes you are important in some real-world way. In those cases, you usually want to condense them into one entry, adding an additional column that indicates how many unique entries there were. Multiple entries for a single entity. This case is a little more interesting than duplicate entries. Often, each real-world entity logically corresponds to one row in the dataset, but some entities are repeated multiple times with different data. The most common causes of this is that some of the entries are out of date and only one row is currently correct. Missing entries. Most of the time, when some entities are not described in a dataset, they have some common characteristics that kept them out. For example, let's say that there is a log of all transactions from the past year. We group the transaction by customer and add up the size of the transaction for each customer. This dataset will have only one row per customer, but any customer who had no transaction in the past year will be left out entirely. In a case such as this, you can join the derived data up against some known set of all customers and fill in the appropriate values for the ones who were missing. Nulls. Null entries typically mean that we don't know a particular piece of information about some entity. The question is why. Most simply, nulls can arise because the data collection process was botched in some way. What is this means depends on the context. When it comes into to do analytics, nulls cannot be processed by many algorithms. In these cases, it is often necessary to replace the missing values with some reasonable proxy. What you will see most often is that it is gauged from other data fields. What you simply plug in the mean of all the non-null values. Huge outliers. Sometimes a massive outlier in the data is there because there was truly an aberrant event. How to deal with that depends on the context. Sometimes the outliers should be filtered out of the dataset. In web traffic, for example, you are usually interested in predicting pages views by humans. A huge spike in recorded traffic is likely to come from a bot attack rather than any activities of humans. Formatting issues. Formatting is irregular between different tables/columns. This happens a lot, typically because of how the data was stored in the first place. It is an especially big issue when joinable/groupable key are irregularly formatted between different datasets. Extra white space. For such a small issue, it is almost comical how often random white space confounds analysis when people try to say join the identifier ABC against ABC for two different datasets. White space is especially insidious because when you print the data to the screen to examine it, the white space might be impossible to discern. Irregular capitalization. Python strings have lower and upper methods which will return a copy of the original string with one letter set to uppercase or lowercase. Inconsistent delimiters. Usually a dataset will have a single delimiter, but sometimes different tables will use different ones. Irregular null format. There are a number of different ways that missing entries are encoded into CSV files, and they should all be interpreted as nulls when the data is read in. Invalid character. Some data files will randomly have invalid bytes in the middle of them. Some programs will throw an error if you try to open up anything that isn't valid text. In these cases, you may have to filter out the invalid bytes. Operating system incompatibilities. Different operating systems have different file conventions, and sometimes that is a problem when opening a file that was generated one OS on a computer that runs a different one. Wrong software versions. Sometimes you will have a file of a format that is designed to be handled by a specific software package. However, when you try to open it, a very mystifying error is thrown. This happens, for example, with data compression formats. Thank you. Hello everyone. Welcome to my lecture, Visualizations and Simple Metrics. A rule of thumb for data science deliverables is this: if there isn't a picture, then you are doing it wrong. Typically, a good analytics project starts with exploratory visualization that help you develop hypotheses and get a feel for the data, and it ends with carefully manicured figures that make the final results visually obvious. The actual number crunching is hidden in the middle, sometimes almost as an aside. I have had a number of projects where there was never even any actual machine learning. People needed to know whether there was signal in the data and which directions were most promising for further work, and graphics showed that more clearly than a number ever could. This fact is very underappreciated outside of the data analysis community. Many people think of data scientists as numerical badasses working black magic from a command line, but that's just not the way the human brain processes data, generates hypotheses, or develops familiarity with an area. Pictures are plans A to C for everything except the last stage of statistically validating results. I have often joked that if humans were able to visualize things in 1,000 dimensions, then my job as a data scientist would consist entirely of generating and looking at scatter plots. This lecture will take you through several of the most important visualizations. You have probably seen most of this before, but it's always good to revisit the basics. We will also cover some exploratory metrics, such as correlations, which capture in crude numerical form some of the patterns that are clear from a good visual. There are many techniques not covered in this lecture, and you would do well to learn them. However, my experience is that these core ones will cover most of your needs. I strongly recommended memorizing the syntax for basic visualization in your programming language of choice. In exploratory analysis especially, it's useful to be able to chug through various ways of visualizing your data without needing to consult a reference on the syntax. There are, however, still times when we need a number. There are two reasons for this. One, our eyes can trick us, so it's important to have a cold hard statistics too. Two, often you don't have time to sift through every possible picture, and you need some way to put a number on it so that the computer can make decisions of some sort automatically. A note on Python's visualization tools. The main visualization tool for Python is a library called matplotlib. While matplotlib is powerful and flexible, it is probably the weakest link in Python's technical stack. The graphs can be a bit cartoonish. In some ways, the syntax is non-intuitive, and the interactivity leaves something to be desired. Most of the appearance issues can be fixed by tweaking a graphics configuration, but the default settings are not great. I am sticking with matplotlib for this lecture because it is by far the most standard tool. It is sufficient for most data science, and it integrates well with the other libraries, but there are other libraries out there that are gaining ground, especially browser based ones such as Bokeh and Plotly. Example code in this lecture will use pandas whenever possible. However, pandas visualization are a wrapper around matplotlib, and sometimes we have to use matplotlib directly. Typically, you make an image by calling the plot method on a pandas object, and pandas does all the image formatting under the hood. Then you use matplotlib's pyplot module for things such as setting the title and the final act of either displaying the image or saving it to a file. Thank you. Hello everyone, welcome to my lecture, Visualization and Simple Metrics, a rule of thumb for Data science deliverables is this: if there isn't a picture, then you are doing it wrong. Typically, a good analytics project starts with exploratory visualization that help you develop hypotheses and get a feel for the data, and it ends with carefully manicured figures that make the final result visually obvious. Example code to illustrate the visualization techniques we discuss in this lecture. We will apply them to the famous iris dataset, which you may have seen in a statistics textbook. It describes physical measurements taken of flower specimens drawn from three different species of iris. There are 150 data points, 50 from each species, and each data point gives the length and width of the petals and sepals. Pie charts. Pity the poor pie chart. I feel like I never see it used in serious applications, almost as if it's locked down on as being too simple. But pie charts are really one of the clearest ways to present data, and I recommend using them whenever they are applicable. Technically, everything you get from a pie chart you could get equally well from looking at a list of numbers, but making sense of the numbers requires cognitive effort and attention. On the other hand, lower level neural circuits make immediate sense of the pie charts. This is perhaps the clearest illustration of the guiding principle behind all visualizations. It's not about conveying information, but about conveying it in a way that the human brain will understand and care about. In my own work, the most mileage I have gotten out of pie chart is when I am either doing exploratory analysis of a data set or communicating the results of a binary classifier. Bar charts. The same information that is in a pie chart could equally will be conveyed in a bar chart. In this particular case, it's actually a much more sensible visualization, since we are interested in the relative sizes of the different flowers rather than how big a slice of the flower pie they each take up. Note the following pieces of Python's plotting syntax that let us tweak the appearances of the figure. 1. The font size. Optional argument controls how big a piece of font is. It's usually too small by default. 2. The rotate optional argument lets us rotate the text. 3. We used subtitle to give the title for the overall figure. Pandas will by default label each subplot with its corresponding column in the data frame being plotted. There are others available if you are trying to make the figures look really polished. Histograms. Histograms are probably my personal favorite visualization tool, partly because it seems like they usually contain something interesting. There are often distinct bumps in the histogram, which might correspond to several distinct classes of real-world entities. You can get a sense of whether there are a few distinct outliers, how much variation is in the population, and so on. A histogram is almost always a meaningful thing to make. It works for floating values or integers, and unlike scatter plots, you only need one numerical field. What jumps out at you is that the petal length has a clearly bimodal distribution, suggesting that this one species has almost categorically longer petals. We can confirm this by plotting each species separately but on the same axis and different colors. There are two big problems that occur with histograms. The first one is the number and size of the bins you use. If the bins are too large, then you can obscure fascinating patterns that occur within a single bucket. If they are too small, then many of your buckets will contain no points, and your bell-shaped curve will turn into a bunch of one-unit high bars. The second problem is that sometimes your data can mar the picture. There might be one bucket that contains so many points, for example, that every other bucket is squeezed down to what looks like noise. There might, for example, be a massive spike at zero point 0.0, and you have to filter out those points before you draw the histogram. The other visual problem is outliers, which can smash the overwhelming majority of the points to the far left of the graph. In some cases, this is pretty simple to deal with. You have a handful of points that are massive outliers, and all you need to do is filter out those points. Thank you. Hello everyone, welcome to my lecture. Means, standard deviations, medians, and quantiles. Sometimes, of course, you must summarize a distribution down to just a few numbers. Usually, these summaries are based on the assumption that your data's distribution is bell-shaped, and your goal is to give some idea of where the peak of the bell is and how widely it spreads. Within this vein, there are two main options. Number one, keep the mean and standard deviation. These are the most historically popular metrics, and they are much easier to compute. 2. Give the median, 25th percentile and 75th percentile. These metrics are more robust to pathologies in the data, but they are computationally more expensive. These numbers all still exist even if your data has multiple peaks in the distribution, but their usual intuitive interpretation breaks down. The other pathology that deserves some discussion is outliers in the data. This isn't a huge problem for medians and quantiles, but it can be game changing with mean and standard deviation. This is shown in the following figure, where I have simulated data from a long normal distribution, made a histogram and plotted the mean as a dashed vertical line. The handful of very large outliers have pulled the mean well to the right of the actual hump in the distribution. Outliers make it very hard to give an intuitive interpretation of the mean, but in fact, the situation is even worse than that. For a real world distribution, there always is a mean, and when we take the average of our data points, we are trying to estimate that mean. But when there are massive outliers, just a single data point is likely to dominate the value of the mean and standard deviation. So much more data is required to even estimate the mean, let alone make sense of it. A common solution is to, before calculating the mean, throw out all data points that are deemed to be outliers. A common criterion is anything below the 25th percentile or above the 75th percentile. This workaround corresponds to the idea that these outliers are pathological data points, which really should be discarded if we are trying to understand the underlying phenomena. If we are dealing with measurements from a physical sensor, for example, they might have been caused by a malfunction of our hardware. In other situations, though, such as the amount of money in a transaction, the outliers are extremely important data points that can't be discarded. The median is not perfect either. In the case of outlier data, or even just a lopsided bell curve, it moves away from the hump in the bell curve. The median also does not change at all if you perturb the outlier values. However, it still keeps it user friendly, meaning half the values are greater and half are less. Personally, I generally use median if I want to know what's typical, but I use mean if the average behavior is really what I care about from a business perspective. Box plots. Box plots are a convenient way to summarize a dataset by showing the median, quantiles, and min/max values for each of the variables. Note that the upper quantile is much farther from the median compared to the lower quantile, and the effect is even more pronounced for the mean and max values. If you just use the histogram outliers, can show up as a deceptively slight increase in the thickness of the tails. Scatter plot. I have often joked that if humans could see things in an arbitrary number of the dimensions, then all of my data science work would consist of making and interpreting scatter plots. In my experience, they are one of the simplest but most powerful ways to visualize relationships within a dataset, so they are a great first step when you are finding your feet with a new project. Scatter plots with logarithmic axes. A key variation on scatter plots is using logarithmic axes. In many applications, the number being plotted are all positive, but they can vary by orders of magnitude. This might happen if you are looking at traffic to a collection of websites, where some sites receive vastly more views than others, or personal income. In a scatter plot of data such as this, all but the largest data points will be squeezed to one side, making the plot essentially unreadable. Thank you. Hello everyone, welcome to my lecture. Machine learning classification. Machine learning classifiers are a critically important part of the data science toolkit. However, they are not nearly as important as they are made out to be. A large part of the mystique of data science comes from the idea that we can pour data into a magical black box that can learn everything about the data and solve business problems. The reality is a lot more mundane. As we have discussed previously, it takes a lot of work to get the data into a form where it can be fed into the black box. It's lot of savvy to point the black box at the right question, and additional work to make sense of the results. The machine learning black box itself is usually just a library that you call. Sure, it's good to have some idea of how the classifiers work under the hood. You can pick better ones to use, avoid common pitfalls, make better sense of their output, and understand how to jury ring them as need be. But training a plain vanilla classifier is often constructed as being rocket science, and it's not. This lecture comes in two sections. After some initial notes, the first will be a series of rapid fire tutorials about some of the most useful classifiers. The second section will discuss the various ways that we can grade their accuracy. What is a classifier and what can you do with it? A machine learning classifier is a computational object that has two stages. Number one, it gets trained. It takes in its training data, which is a bunch of data points and the correct level associated with them, and tries to learn some pattern for how the points map to the levels. 2. Once it has been trained, the classifier acts as a function that takes in additional data points and outputs predicted classification for them. Sometimes the prediction will be a specific level, other times it will give a continuous valued number that can be seen as a confidence score for a particular level. There are two big use cases for classifier. The first is the obvious one. We have things that need to be classified. This happens all the time in production code situations where a computer has to decide, say, which ad to show a user. It also happens when computers aren't making decisions autonomously, but instead flagging things for a flesh and blood human to look at, flagging potential instances of credit card fraud, for example. The other use for classifier is to give insights about the underlying data. In my own career, this has actually been the more common use case. My clients have not been so interested in predicting, say, that a particular machine will fail. What they really want to know is the patterns in the data that predict failures, because those patterns can help them diagnose and fix something that's going wrong on their assembly line. In cases such as this, we want to dissect our classifiers after the fact, extracting business insights. This becomes an interesting balancing act for a data scientist. Sometimes the most accurate classifiers are the hard set to make real world sense of. A few practical concerns. The whole notion of machine learning classification is premised on the idea of having correctly labeled training data and in sufficient quantities to train our classifier. However, this is luxury that the real world often doesn't afford. For example, in fraud detection, you will probably have a modest size set of hand-labeled fraud cases and a huge mass of unlabeled data. You just presume that those unlabeled points are non-fraudulent, which means that an unknown fraction of your training data is mislabeled. It's not like the hand-labeled fraud cases are a nice random sample from all fraud cases. They represent whatever kind of fraud people may have been looking for so far. There could easily be whole new category of fraud, every instance of which is labeled as non-fraud in your training data. Thank you. Hello everyone, welcome to my lecture. A few practical concerns. The whole notion of machine learning classification is premised on the idea of having correctly labeled training data and in sufficient quantities to train our classifier. However, this is a luxury that the real world often doesn't afford. For example, in fraud detection, you will probably have a modest size set of hand-labeled fraud cases and a huge mass of unlabeled data. You just presume that those unlabeled points are non-fraudulent, which means that an unknown fraction of your training data is mislabeled. It's not like the hand-labeled fraud cases are a nice random sample from all fraud cases. They represent whatever kind of fraud people have been looking for so far. There could easily be whole new categories of fraud, every instance of which is labeled as non-fraud in your training data. What even is fraud anyway? In many cases, you have to come up with the training data yourself, and it's not a priori clear how things should be labeled. An email about Nigerian princess is almost certainly fraud, but what about somebody selling discount Viagra? In many cases, where I'm looking for cool patterns rather than the classifier themselves, what I will often do is remove edge cases from my training data. For example, I once had a client who was trying to understand customer loyalty, and I was writing a classifier for whether or not they would lose a customer within the next year. The problem is that customers don't announce they are leaving. They just stop using my client services, which most customers don't use all that often anyway. What I did was to formulate criteria for customers being definitely still loyal and another for them being definitely not loyal. Every gray area customer who didn't fall into one of those categories was discarded before training. They made up around a third of customers. The resulting classifier worked surprisingly well, but the really exciting part was that when we applied it to the gray area customers, those that were flagged as higher risk did indeed come closer to satisfying the not loyal criteria compared to the loyal criteria. This suggested that the gray area customers were more or less extreme versions of what the other customers were doing, rather than some fundamentally new category of people. This question of defining ground truth is beside the perennial problem of data science, feature extraction. Binary versus multi-class. Most classification problems have a binary classification, 1 or 0, yes or no. However, oftentimes the label is a categorical variable, capable of talking on several values. There are some classifier algorithms that handle this situation natively, but many others are strictly binary. when you are using a classifier that is binary but solving a problem that has k possibly labeled. The standard solution is to actually train k different classifiers, one for each level x, classifying points as being x or something else. For the most part, these distinctions are wrapped up within machine learning libraries and invisible to data scientists who use the libraries. Explanation in this lecture will freely assume that classifiers are all binary. Example script. The following script demonstrates many of the topics we will cover in this lecture in a realistic setting using the sample iris dataset from the last lecture. It takes several important classifiers, trains each one to distinguish Iris virginica from the other species, and then plots the results on a rock curve. Each of these classifiers and the metrics we use to evaluate them will be explained later. Thank you. Hello everyone, welcome to my lecture, Specific Classifiers. The world is full of different classification algorithms. This section will go over some of the most useful and important ones. Decision trees. A decision tree is conceptually one of the simplest classifiers available. Using a decision tree to classify a data point is the equivalent of following a basic flowchart. It consists of a tree structure such as the following. Every node in the tree asks a question about one feature of a data point. If the feature is numerical, the node asks whether it is above or below a threshold, and there are child nodes for yes and no. If the feature is categorical, typically there will be a different child node for every value it can take. A leaf node in the tree will be the score that is assigned to the point being classified. It doesn't get much simpler than that. Using a decision tree is conceptually quite straightforward, but training one is another matter entirely. In general, finding the optimal decision for your training data is conceptually intractable. So in practice, you train the tree with a series of heuristics and hope that the result is close to the best tree possible. Generally, the algorithm is something along these lines. Number 1. Given your training data X, find the single feature bracket and cut off for the feature if it's numerical bracket close that best partitions your data into classes. Number 2. There are a variety of ways to quantify how good a partition is. The most common ones are the information gain and the Gini impurity. I won't delve into their precise meanings here. 3. The single best feature becomes the root of your decision tree. 4. Recursively train each of the child nodes on its partition of the data. 5. The recursion stops when either all of the data points in your partition have the same level or the recursion has gone to a predetermined maximum depth. At that point, the scores stored in this node will just be the breakdowns of the levels in the partition. You will probably never need to worry about the details of how to train a decision tree, but knowing the basic process helps to understand one of the biggest problems with this classifier: overfitting. If you set the maximum depth too far, for example, every leaf node will end up with a partition that contains only a few points, all of which have the same level. This will result in the decision tree constantly giving out extremely confident scores that realistically are just an accident of small numbers. You can set parameters on your decision tree that force it to terminate when, say, the best partition on a node are too small. But in many libraries, the default setting will let a decision tree drastically overfit itself, so you should be aware of this and tune your trees accordingly. Decision trees are very easy to understand, so it's perhaps a bit surprising that they are often difficult to tease real world insights out of. Looking at the top few layers is certainly interesting and suggests what some of the more important features are, but it's not always clear what the features and their offs mean to the real world, unless you want to wade into the deep waters of dissecting the Guinea impurities from the training stage. Even if you do this, there is still a very real risk that the same feature will wait toward hits at one node of the tree and toward non-hits at another node. What the heck does that mean? Personally, I don't use decision trees much for serious work. However, they are extremely useful for their human readability. This is especially handy if you are working with people who don't know machine learning and are wary of black boxes and the rapidity with which they can do classifications. Above all, decision trees are useful as a building block for constructing random forest classifiers, which I will discuss in the next section. Thank you. Hello everyone, welcome to my lecture. Support vector machines. Support vector machines are one of the few classifiers that are fundamentally binary. They don't give continuous valued scores that can be used to assess how confident the classifier is. This makes them annoying if you are looking for business insight and unusable if you need to have the notion of a gray area. That said, they are popular for a reason. They are intuitively simple, mathematically elegant, and trivial to use. Plus, those unprincipled hacks I mentioned earlier can be incredibly powerful if you pick the right one. The key idea of an SMB is illustrated in the following figure. Essentially, you view every data point as a point in d-dimensional space and then look for a hyperplane that separates the two classes. The assumption that there actually is such a hyperplane is called linear separability. Training the SVM involves finding the hyperplane that separates the datasets and is in the middle of the gap between the two classes. Specifically, the margin of a hyperplane is mean. And you pick the hyperplane that maximizes the margin. Mathematically, the hyperplane is specified by the equation fx is equal to w dot x plus v is equal to 0, where w is a vector perpendicular to the hyperplane and b measures how far offset it is from the origin. To classify a point x, simply calculate fx and see whether it is positive or negative. Training the classifier consists of finding the w and b that separates the dataset while having the largest margin. This version is called hard margin SVM. However, in practice, there often is no hyperplane that completely separates the two classes in the training data. Intuitively, what we want to do is find the best hyperplane that almost separates the data by penalizing any points that are on the wrong side of hyperplane. This is done using soft margin SVM. The other killer problem with SVM is if you have as many features as data points. In this case, there is guaranteed to be a separating hyperplane regardless of how the points are labeled. This is one of the curses of working in high dimensional space. You can do dimensionality reduction as a pre-processing step, but if you just plug high dimensional data into an SVM, it is almost guaranteed to be grossly overfitted. The most notorious problem with a plain SVM is the linear separability assumption. An SVM will fail utterly on a dataset as the following. There is no line between the two classes of points. The pattern is clear if you just look at it. One class is near the origin and the other is far from it, but an SMB can't tell. The solution to this problem is a very powerful generalization of SVM called kernel SVM. The idea of kernel SVM is to first map our points into some other space in which the decision boundary is linear, and then construct a support vector machine that operates in that space. For the previous figure, if we plot the distance from the origin on the x-axis and the angle 0 on the y-axis, we get the following figure. The data here is linearly separable. In general, kernel SVM requires finding some function that maps our points in d-dimensional space to points in some n-dimensional space. In the example I gave, n and d were both 2, but in practice we usually want n to be larger than d to increase the chances of linear separability. If you can find pi, then you are golden. Most kernel SVM frameworks will let users define their own functions as well. If you take this route, you should be aware that it's a bit technical to make sure that k is a valid kernel function, that is, that it has a corresponding mapping phi. Most simply, k has to be symmetric. K bracket xy is equal to k bracket yx for any x and y. The major constraint though is that it be positive defined. This is a highly technical constraint that I won't get into here. Thank you. Hello everyone, welcome to my lecture, Logistic Regression. Logistic regression is a great general purpose classifier, striking an excellent balance between accurate classification and real world interpretability. I think of it as kind of a non-binary version of SVM, one that scores points with probabilities based on how far they are from the hyperplane, rather than using that hyperplane as a definitive cutoff. If the training data is almost linearly separable, then all points that aren't near the hyperplane will get a confident prediction near 0 on or on. But if the two classes bleed over the hyperplane a lot, the prediction will be more muted, and only points far from the hyperplane will get confident scores. In logistic regression, the score for a point will be px equal to 1 by 1 plus expectation bracket w into x plus b. Note that expectation bracket w into x plus b is the same fx we saw in SVM, where w is a vector that gives weights to each feature and b is a real valued offset. With SVM, we look at whether fx is positive or negative, but in this case we plug it into the so-called sigmoid function z equal to 1 by 1 plus expectation z. As with SVM, we have a dividing hyperplane defined by w into x plus b equal to 0. In SVM, that hyperplane is the binary decision boundary, but in this case it is the hyperplane along which px equal to 1 by 2. The sigmoid function shows up a few places in machine learning, so it makes sense to dwell on it a bit. If you plot out x, it appears as following. You can see that pi 0 is 0.5. As the argument blows up to infinity, it approaches 1.0, and as it goes to negative infinity, it goes 0.0. Intuitively, this makes it a great way to take confidence weights and cram them down into the interval where they can be treated as probabilities. The sigmoid function also has a lot of convenient mathematical properties that make it easy to work with. We will see it again in the section on neural networks. Pulling real world meaning out of a trained logistic regression model is easy. If the KTH component of W is large and positive, then the KTH feature being big suggested that the correct level is 1. If the kth component of W is large and negative, then the kth feature being big suggests that the correct level is 0. The larger the elements of W are in general, the tighter our decision boundary and the more closely we approach an SVM. Lasso regression. Lasso regression is a variant of logistic regression. One of the problems with logistic regression is that you can have many different features, all with modest weights, instead of a few clearly meaningful features with large weights. This makes it harder to extract real world meaning from the model. It is also an insidious form of overfitting, which is beginning to have the model generalize poorly. In lasso regression, Px has the same functional form of pi bracket w into x plus b. However, we train it in a way that punishes modest size weights. The numerical algorithm that finds the optimal weights generally doesn't use heuristics or anything. It's just cold numerical tracing. However, as an aid to human intuition, I like to think of some example of heuristics that the solver might in effect employ. If features I and j have large weights, but they usually cancel each other out when classifying a point, set both their weights to 0. If features I and j are highly correlated, you can reduce the weight for one while increasing the weight for the other and keeping prediction more or less the same. The end result of all this tends to be having most of the feature weights go to 0, while only a few of the most significant features have non-zero weights. Thank you. Hello everyone, welcome to my lecture. Naive Bayes. Bayesian statistics is one of the biggest, most interesting and most mathematically sophisticated areas of machine learning. However, most of that is in the context of Bayesian networks, which are a deep, highly sophisticated family of models that you typically don't see in normal data science. Data scientists are more likely to use drastically simplified version called naive Bayes. I talk in more detail about Bayesian statistics in the lecture on statistics. Briefly though, a Bayesian classifier operates on the following intuition. You start off with some initial confidence in the levels 0 and 1. When new information becomes available, you adjust your confidence levels depending on how likely that information is conditioned on each level. When you have gone through all available information, your final confidence levels are the probabilities of the levels 0 and 1. Okay, now let's get more technical. During the training phase, a naive Bayesian classifier learns two things from the training data: how common every level is in the whole training data. For every feature x, its probability distribution when the level is 0. For every feature x, its probability distribution when the level is 1. The last two are called the conditional probabilities, and they are written as PR bracket xi equal to xi, y equal to 0, bracket close. Another one, PR bracket xi equal to xi, y equal to 1, bracket close. When it comes time to classify a point x equal to x1, x2, xd, the classifier starts off with confidence. There are a lot of things here that need fleshing out of if you are implementing a naive Bayes classifier. For example, we need to assume some functional form of PR such as a normal distribution or something. In order to fit it during the training stage, we also need to be equipped to deal with overfitting there. But the biggest problem is that we are treating x, y as being independent of every other xj. For example, our data might be such that x5 is just a copy of x4. In that case, we really shouldn't adjust our confidences when we get to x5, since x4 had already accounted for it. Naive Bayes classifiers completely ignore this possibility. So it's perhaps surprising that they tend to be very powerful classifier. The way I think of it is this: imagine the situation I described where x4 and x5 are identical, so we essentially double count x4. If x4 is a powerful predictive variable, then this might make us overconfident, but it usually doesn't make us wrong. Neural nets. Neural nets used to be the black sheep of classifiers, but they have enjoyed a renaissance in recent years, especially the sophisticated variants collectively known as deep learning. Neural nets are as massive an area as Bayesian networks, and many people make careers out of them. However, basic neural nets are standard tools that you see in machine learning. They are simple to use, fairly effective as classifiers, and useful for teasing interesting features out of a dataset. Neural nets were inspired by the workings of the human brain, but now that we know more about how biological circuits work, it's clear that that analogy is bunk. Really sophisticated deep learning is at the point where it can be compared to some parts of real brains, but anything short of that should be thought of as just another classifier. The simplest neural network is the perceptron. A perceptron is a network of neurons, each of which takes in multiple inputs and produces a single output, and the level nodes correspond to either the input variables to a classification or a range of output variables. The other nodes are neurons. The neurons in the first layer take all of the raw features as inputs. Their outputs are fed as inputs to the second layer, and so on. Ultimately, the outputs of the final layer constitute the output of your program. All layers of neurons before the last one are called hidden layers. Unlike other classifier, neural networks very organically produce an arbitrary number of different outputs, one for each neuron in the final layer. In this case, there are 3 outputs. In general, you can use neural nets for tasks other than classification and treat the outputs as a general purpose numerical vector. In classification tasks, though, we typically look at the ith output as the score for the ith category that a point can be classified as. Thank you. Hello everyone, welcome to my lecture, Clustering and Dimensionality Reduction. This lecture is about techniques for studying the latent structure of your data in situations where we don't know a priori what it should look like. They are often called unsupervised learning because, unlike classification and regression, the right answers are not known going in. There are 2 primary ways of studying a dataset's structure: clustering and dimensionality reduction. Clustering is an attempt to group the data points into distinct clusters. Typically, this is done in the hopes that the different clusters correspond to different underlying phenomena. For example, if you plotted people's height on the x-axis and their weight on the y-axis, you would see 2 more or less clear blobs corresponding to men and women. An alien who knew nothing else about human biology might hypothesize that we come in 2 distinct types. In dimensionality reduction, the goal isn't to look for distinct categories in the data. Instead, the idea is that the different fields are largely redundant, and we want to extract the real underlying variability in the data. The idea is that your data is d-dimensional, but all of the points actually only lie on a k-dimensional subset of the space, plus some d-dimensional noise. For example, in 3D data, your points could lie mostly just along a single line or perhaps in a curved circle. Real situations, of course, are usually not so clean-cut. It's more useful to think of k dimensions as capturing most of the variability in the data, and you can make k larger or smaller depending on how much of the information you want to reproduce. A key practical differences between clustering and dimensionality reduction is that clustering is generally done in order to reveal the structure of the data, but dimensionality reduction is often motivated mostly by computational concerns. For example, if you are processing sound, image, or video files, D is likely to be tens of thousands. Processing your data then becomes a massive computational task, and there are fundamental problems that come with having more dimensions compared to data points. In these cases, dimensionality reduction is a prerequisite for almost any analytics you might want to do, regardless of whether you are actually interested in the data's latent structure. The curse of dimensionality. Geometry in high dimensional space is weird. This is important because a machine learning algorithm with D features operates on feature vectors that live in D dimensional spaces. D can be quite large if your features are, say, all of the pixel values in an image. In these cases, the performance of these algorithms often start to break down, and this decay is best understood as a pathology of high dimensional geometry, the so-called curse of dimensionality. The practical punchline to all of this is that if you want your algorithms to work well, you will usually need some way to cram your data down into a lower dimensional space. There's no need to dwell too much on the curse of dimensionality. Thinking about it can hurt the heads up as three-dimensional beings. But if you are interested, I would like to give you at least a teeny taste of what goes on in high dimensions. Basically, the problem is that in high dimensions, different points get very far away from each other. To illustrate the following code, let's set D as a parameter. It then generates 1,000 random points in the unit cube, calculates the distance from every point to every other point, and shows a histogram of those distances for D equal to 2 and D equal to 50. You can see that for D equal to 500, 2 points in the cube are almost always about the same distance from each other. If you did a similar simulation with spheres, you would see that almost all the mass of a high dimensional sphere is in its crust. Sounds weird? Well, yes, it is. That's why we reduce dimensions. Thank you. Hello everyone, welcome to my lecture. Example: eigenspace for dimensionality reduction. The following script will dive right into a lot of the material that we will cover in this lecture. It loads in a sample data of images of 64 into 64 pixel faces with 10 pictures each of the 40 different people. That's D equal to 64 into 64 equal to 4096 dimensions. It then clusters the images, prints out a measure of how distinct the clusters are from each other, and then prints out a measure of how closely the identified clusters line up with the identities of the humans pictured. Then the script uses a technique called principal component analysis, which we will go over in this lecture, to reduce the 4096 dimensional images down to a standard 25 dimensions and redoes the analysis. It finds that the identified clusters match up slightly better with the humans being pictured. In the interest of visualizing the data itself, you can continue the analysis with the following script in order to get better insight into the PCA process. It shows a picture of one of the raw images and then displays the first two called eigenfaces that were identified. PCA tries to model every picture in the dataset as a mixture of the most important eyes and faces. So visualizing them can give us an idea of how the faces vary across the dataset. Finally, it shows a graph called a script plot, which plots out the importances of the different eyes and faces. Principal component analysis and factor analysis. The granddaddy of dimensionality reduction algorithms is, without question, principal component analysis, or PCA. Geometrically, PCA assumes that your data in d-dimensional space is football-based, shaped, and ellipsoidal blob that is stretched out along some axes, narrow in others, and generally free of any massive outliers. Take the following image for example. Intuitively, the data is rarely one-dimensional, lying on the line x equal to y, but there is some random noise that slightly perturbs each point. Rather than giving the two features x and y for each point, you can get a good approximation with just the single feature x plus y. There are two ways to look at this. Number one, intuitively, it seems that x plus y might be the real world feature underlying the data, while x and y are just what we measured. By using x plus y, we are extracting a feature that is more meaningful than any of our actual raw features. Technically, it is more computationally efficient to process one number rather than two. If you wanted, in this case, you could estimate x and y pretty accurate if you only know x plus y. Numerically, using one number rather than two lets us shy away from the curse of dimensionality. PCA is a way of, number one, identifying the correct features such as x plus y that capture most of the structure of the dataset, and number two, extracting these features from the raw data points. To be a little more technical, PCA takes in a collection of d-dimensional vectors and finds a collection of d principal component vectors of length 1 called p1, p2 and pd. A point x in the data can be expressed as x equal to a1 into p1 plus a2 into p2 plus plus ad into pd. However, the pi are chosen so that generally a1 is much larger than the other a1, a2 is larger than a3 and above, etc. So realistically, the first few pi capture most of the variation in the dataset, and x is a linear combination of the first few pi and some small correction terms. The ideal case for PCA is something where large swath of features tend to be highly correlated, such as photograph where adjacent pixels are likely to have similar brightness. So our example script was an excellent candidate. The code in our script that performed the PCA analysis and reduced the dataset's dimension is PCA equal to PCA bracket 25. Note that in this case we have passed the number of components we want to extract as a parameter in PCA. Under the hood, it's much more computationally efficient to only extract the first few components. So that's good to do if you don't need entire PCA decomposition. Thank you. Hello everyone, welcome to my lecture, Script Plots and Understanding Dimensionality. In our motivation for PCA, we suggested that the dataset was rarely one-dimensional and that one of the goals of PCA is to extract that real dimensionality of a dataset by seeing how many components it took to capture most of the dataset's structure. In reality, it's rarely that clear. What you get instead is that the first few components are the most important, and then there is a gentle taper into uselessness as you go further out. It is common to plot out the importance of the different principal components. Technically, the importance is measured as the fraction of a dataset's variance that the component accounts for in what's called a script plot, which we generated earlier. Eyeballing this plot, I would venture that the face dataset is more or less 15 dimensions. It's still a lot, but much less than the 4096 dimensions in the raw data. Factor analysis. I should note that PCA is related to the statistical technique of factor analysis. Mathematically, they are the same thing. You find a change of coordinates where most of the variance in your data exists in the first new coordinate, the second most in the second coordinate, and so on. The divergent terminology is mostly an accident of the fact that they were developed independently and applied in very different ways to different fields. In PCA, the idea is generally dimensionality reduction. You find how many of these new coordinates are needed to capture most of your data's variance, and then when you reduce your data points to just those few coordinates, a prototypical application of PCA is analyzing pictures of faces. There is a staggering number of dimensions in the data, which are almost entirely redundant, and examining the principal components themselves gives insights into the behavior of the system. Factor analysis, on the other hand, is more about identifying causal factors that give rise to the observed data. A major historical example is in the study of intelligence. Tests of intelligence in many different areas were seen to be correlated, suggesting that the same underlying factors would affect intelligence in many different areas. Researchers found that a single so-called G-factor accounts for about half of the variance between different intelligence tests. This lecture generally looks at things from a PCA perspective, but you should be aware that both viewpoints are useful. Limitations of PCA. There are three big gotchas when using PCA. Number 1. Your dimensions all need to be scaled to have comparable standard deviations. If you arbitrarily multiplied one of your features by 1,000, then PCA will consider that features to contribute much more to the dataset variance. Number 2. PCA assumes that your data is linear. If the real shape of your dataset is that it's bent into an arc in high dimensional space, it will get blurred into several principal components. PCA will still be useful for dimensionality reduction, but the components themselves are likely not be very meaningful. 3. If you are using PCA on images of faces or something similar, the key parts of the pictures need to be aligned with each other. PCA will be one of no use if, for example, the eyes are covered by different pixels. If your pictures are not aligned, doing automatic alignment is outside the skill set of most data scientists. Thank you. Hello everyone, welcome to my lecture. Regression. Regression is similar to classification. You have a number of input features and you want to predict an output feature. In classification, this output feature is either binary or categorical. With regression, it is a real valued number. Typically, regression algorithms fall into two categories: modeling the output as a linear combination of the inputs. There is a ton of elegant math here and principled ways to handle data pathologies. 2. Ugly hacks to deal with anything nonlinear. This lecture will review several of the more popular regression techniques in machine learning, along with some techniques for assessing how well they performed. I have made the unconventional decision to include fitting a line to two-dimensional data within the lecture on regression. You usually don't see curve fitting in the context of machine learning regression, but they are really the same thing mathematically. You assume some functional form for the output as a function of the inputs, and then you choose the parameters to line up as well as possible with your training data. The distinction between them is a historical accident. Fitting a curve to data was developed long before machine learning and even before computers. Least squares. The simplest example of regression is one that you probably saw in high school: the fitting a line to data. You have a collection of x by y pairs and you try to fit a line to them of the form y equal to mx plus b. I remember back in school being encouraged to plot the points out, fit a line to them by eye, trace the line with a ruler, and use that to pull out m and b. On some level, I think that's the best way to do it, because the human eye can account for outliers and instantly notices data pathologies. Recall Anscombe's quartet, where each of the four datasets has the same line of best fit and the same quality of fit, at least using the standard methods. However, we also need an objective way to pull out a number, and one that can be done by a computer without human intervention. The standard way to fit a line is called least squares. In Python, it can be fit using the linear regression class in the example scripts, and the fit coefficients can be found in the following way. Least squares work by picking the value of m and b that minimize the penalty of function, which adds up an error term across all of the points. The key thing to understand here is that this penalty function makes least squares regression extremely sensitive to outliers in the data. 3 deviations of size 5 will give a penalty of 75, but just a single larger deviation of size 10 will give the larger penalty of size 100. Linear regression will bend the parameters so as to avoid large deviation of even a single point, which makes it unsuitable in situations where a handful of large deviations are to be expected. An alternative approach that is more suitable to data with outliers is to use the penalty function, where we just take the absolute values of the different error terms and add them. This is called L1 regression, among other names. Outliers will still have an impact, but it is not as egregious as with least squares. On the other hand, L1 regression penalizes small deviations from expectation more harshly compared to least squares, and it is significantly more complicated to implement computationally. Fitting nonlinear curves. Fitting a curve to data is a ubiquitous problem not just in data science but in engineering and the sciences in general. Often there are good a priori reasons that we expect a certain functional forms, and extracting the best fit parameters will tell us something very meaningful about the system we are studying. A few examples that I have seen included the following: exponential decay to some baseline. This is useful for modeling many processes where a system starts in some kind of agitated state and decays to baseline. Logistic growth, which is useful in biology for modeling the population density of organisms growing in a constrained environment that can only support so many individuals. Thank you. Hello everyone, welcome to my lecture. Fitting non-linear curves. Fitting a curve to data is a ubiquitous problem not just in data science but in engineering and the sciences in general. Often there are good a priori reasons that we expect a certain functional form, and extracting the best fit parameters will tell us something very meaningful about the system we are studying. A few examples that I have included the following. 1. Exponential decay to some baseline. This is useful for modeling many processes where a system starts in some kind of aggregate state and decays to a baseline. Y equal to ae to the power minus bx plus 3. 2. Exponential growth. Y equal to ae to the power bx. 3. Logistic growth, which is useful in biology for modeling the population density of organisms growing in a constrained environment that can only support so many individuals. Y equal to a e to the power bx by c plus e to the power bx. 4. Polynomials of various degrees. Y equal to a0 plus a1 into x plus a2 into x square. Least squares is the typical approach in all of these cases where we pick the parameters to minimize the penalty function. In Python, the way to do general least square fitting is with the curve fit function shown in the following code. It takes as its first argument a user defined function which takes in x and some number of additional parameters, uses those parameters to calculate some function of x and returns the value. The next arguments are the x values and y values of the data we have. Then curve fit through a process of trial and error called optimization tries to find the values of the additional parameters that will minimize the error term for the given x and y values. It returns a tuple of two things, the best fitted parameters and a matrix that estimates how much they vary. I should note that computationally doing non-linear fits such as this is extremely slow, and the numerical algorithms can sometimes go horribly awry and give incorrect results. The best way to address this, if you can, is to transform your problem into a linear one by fitting a line to some function of your data. If that is not possible, you can often improve the performance by inputting an initial guess as an optional parameter. In curve fit, that optional argument is called p0. Goodness of fit, R square and correlation. When you are assessing the quality of a fitted curve, there are two questions we want to answer. 1. How accurately can we predict values? 2. We assumed that the data followed some functional form. Was that even a good assumption? The standard way to answer the first of the questions is called R2. Pronounced R squared, R2 is often described as the fraction of the variance that is accounted for by the model. A value of 1.0 means a perfect match, and a value of 0 means you didn't capture any of the variation. In some cases, it can even take on negative values. If you want to get a bit more detailed, the calculation of R2 is based on two concepts, where y is the average of all y values in your data, the residual variation. This allows us to say in a precise sense that your fitted model accounts for a certain percentage of the variation in the data, and you can see it as the fraction of all variation that is captured by the model. Of course, taking the squares of the residuals isn't necessarily the right way to quantify variation, but it is the most standard option. Despite looking like a square, technically R square can be negative if your model is truly abysmal. Having R square equal to 0 is what you would see if you just define your fitted function to return the average of y as a constant value. You can think of this as the crudest way to fit a function to data. Do any worse than this and your R square will go negative. Another way to quantify your goodness of fit is to simply take the correlation between your predicted values and the known values in the test data. This has the advantage that you can use Pearson, Superman or Kendall correlation depending on how you want to deal with outliers. On the other hand, though, correlation just measures whether your prediction and target values are related. It doesn't measure whether they actually match up. Thank you. Hello everyone, welcome to my lecture. Correlation of residuals. The main ways to measure goodness of fit in regression situation are R-square and correlation between predictions and targets. You typically don't see people asking about whether the functional form being assumed was actually the correct form. If you are fitting two-dimensional data, though, this question can be addressed as well. The simplest way to assess the quality of our model form is to plot the known data against a curve of the predicted values. Do they match up? In Anscombe's quartet, for example, it is visually clear that a linear model is the correct way to approach the first dataset, but the wrong way to approach the second one. A way to quantify this relationship is the so-called correlation of residuals. Intuitively, if our model form is correct, the observed data should be our best fit formula plus some random noise. In that case, the actual data would be randomly above or below our curve. On the other hand, if our model form was bad, we would expect long stretches where the data was systematically higher or lower than our curve. This suggests that we look across our data points sorted by X and calculate the correlation between the consecutive residuals. A correlation near zero suggests that our model form was good, and any failure of its predictive power comes from true noise in the data rather than a failure to pick the right functional form. Linear regression. Now let's move on from fitting a curve and into topics that fit more firmly under the machine learning umbrella. First up, linear regression. Linear regression is the same process as fitting a line to data, except that we say y equal to b plus m1 x1 plus m2 x2 plus dot 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 plus md xd, where d is the number of input features we have. Most of the previous section carry over directly to this more general case. We feed the data using least squares. We quantify performance using R2, and we can also use correlation between predicted and actual values. The first big difference is that it's no longer practical to plot the predicted curve against the actual data points. What you can do instead is to make a scatter plot between the known test values and the values predicted for those test data points. This allows us to gauge whether our model performs better for larger or smaller values and whether it suffers from major outliers. To illustrate the aforementioned example, script will generate this figure for the linear regression model. We can see that there is a clear correlation between the predicted and actual numbers, but it is fairly tenuous. In particular, we can see that there are a number of data points where the actual value was substantially below our predictions. That is, their diabetes was significantly less damaging than we would have guessed based on the other measurements. In fact, the fit line as a whole looks slightly more shallow than the data itself. Together, they suggest that there are a number of anomalously low data points which are pulling our overall predictions lower than perhaps they should be. The other thing that we can do with linear regression is use it to identify features in the data that are particularly interesting. In the example script, we used the normalize function to scale all the features so that they had mean 0 and standard deviation 1. This means that by looking at the relative size of their weights in the linear model, we can get a sense of how related they are to the progression of diabetes. In the example script, I print out the coefficients. This suggests that the third and fourth features are particularly interesting. If we want to zero in on and examine their relationship to diabetes more closely. Thank you. Hello everyone, welcome to my lecture. Natural language processing. Natural language processing is a collection of techniques for working with human language. Examples would include flagging emails as spam, using Twitter to assess public sentiment, and finding which text documents are about similar topics. NLP is an area that many data scientists never actually need to touch, but enough of them end up needing it, and it is sufficiently different from other subjects that it deserves a lecture. This lecture will start with several generic selections about NLP datasets and big picture concepts. Then I will switch gears to the core NLP concepts, moving from the simple, quick and dirty techniques to more complicated ones. I also want to emphasize that NLP techniques are not strictly limited to language. I have also seen them used to parse computer log files, figuring out what sentences the computer generates. Personally, I first learned many of these statistical techniques which working with bioinformatics. Do I even need NLP? The first question to ask when using NLP is whether you even need it. There is often pressure from customers and bosses to solve problems using NLP because it is seen as some kind of magical silver bullet. But in my experience, NLP is hard to implement and it is prone to bizarre errors that are obviously wrong when a human looks at them. I have seen people bang their heads against a problem using NLP techniques, only to eventually give up and try solving the problem with regular expressions. Then, lo and behold, the regular expressions work better than the NLP ever did. Here are a few thoughts to keep in mind when deciding whether to try NLP. If your data has a regular structure to it, then you can probably extract what you need without NLP. NLP tends to be very effective at tasks such as determining whether two documents have similar content, because simple things such as word frequency are very informative. If you are trying to extract facts from documents, it is almost impossible unless you have standardized language such as Wikipedia or legal contracts. You probably can't do it with something such as Twitter. It is often hard to make sense of why an NLP algorithm performed in the way it did. NLP typically requires a lot of training data. The Great Divide: language versus statistics. There are two very different schools of thought in NLP, which use very different techniques and sometimes are even at odds with one another. I will call them statistical NLP and linguistic NLP. The linguistic school focuses on understanding language as language, with techniques such as identifying which words are verbs or parsing the structure of a sentence. This sounds great in theory, but it is often staggeringly difficult in practice because of the myriad ways that humans abuse their languages and break the rules. The statistical school of NLP solves this problem by using massive corpuses of training data to find statistical patterns in language. They might notice that dog and bark tend to occur frequently together, or that the phrase Nigerian prince is more common in a corpus of emails than chance would dictate. Personally, I see statistical NLP mostly as a blunt force work around for the fact that linguistic NLP is so extraordinarily difficult. In the modern era of massive data sets, this divide has become more pronounced, and statistical NLP tends to have the advantage The best machine translation engines, such as ones Google might use to automatically translate a website, are primarily statistical. They are built by training on thousands of examples of human-done translation, such as newspaper articles published in multiple languages or books that were translated. Some linguistics protest that this is dodging the scientific problem of figuring out how the human brain really processes language. Of course, it is, but the bottom line is that the results are generally better. On the other hand, training something like that requires a training corpus and especially craft machine learning algorithm that is generally beyond the reach of all but the most sophisticated NLP users. Thank you. Hello everyone, welcome to my lecture. Example: sentiment analysis on stock market articles. The following script shows off a teeny taste of what is possible with Python's most popular NLP library. You set the sticker symbol of a stock near the top of the script. It then parses a bunch of recent articles about the stock, gauges them as positive or negative, and prints how many fell into each category. Software and datasets. NLP processing is generally very computationally inefficient. Even something as simple as determining whether a word is a noun requires consulting a lookup table containing a language's entire lexicon. More complex tasks such as parsing the meaning of a sentence require figuring out a sentence's structure, which becomes exponentially more difficult if there are ambiguities in the sentence. This is all ignoring things such as typos, slang, and breaking grammatical rules. You can partly work around this by training stupider models on very large datasets, but this will just balloon your data size problems. There are a number of standardized linguistic datasets available in the public domain. Depending on the dataset, they catalog everything from the definitions of words to which words are synonyms of each other to grammatical rules. Most NLP libraries for any programming language will leverage at least one of these datasets. One lexical database that deserves special mention is WordNet. WordNet covers the English language, and its central concept is the scene set. A scene set is a collection of words with roughly equivalent meanings. Casting every word to its associated scene set is a great way to compare whether, for example, two sentences are discussing the same material using different terms. More importantly, an ambiguous word such as run, which has many different possible meanings, is a member of many different scene sets. Using the correct scene set for it is a way to eliminate ambiguity in the sentence. Personally, I think of scene sets as the words of a separate language, one in which there is no ambiguity and no extraneous synonyms. Central concept: bag of words. Probably the most basic concept in NLP, aside from some very high level application of it, is that of a bag of words, also called a frequency distribution. It's a way to turn a piece of free text into a numerical vector that you can plug into a machine learning algorithm. The idea is quite simple. There is a dimension in the vector for every word in the language, and a document's score in the ninth dimension is the number of times the nth words occurs in the document. The piece of text then becomes a vector in a very high dimensional space. Most of this lecture will be about extensions of the bag of words model. I will briefly discuss some more advanced topics, but the reality is that data scientists rarely do anything that can't fit into the bag of words paradigm. When you go beyond bag of words, NLP quickly becomes a staggeringly complicated task that is usually best left to specialists. My first ever exposure to NLP was as an intern at Google, where they explained to me that this was how part of the search algorithm worked. You condense every website into a bag of words and normalize all the vectors. Then when a search query comes in, you turn it into a normalized vector too, and then take it dot product with all of the web page vectors. This is called the cosine similarity, because the dot product of two normalized vectors is just the cosine of the angle between them. The web pages that had high cosine similarity where those whose content mostly resembled the query, that is, they were the best search result candidates. The majority of this lecture will be about extension and refinements of the basic idea of bag of words. We will discuss some of the more intricate sentence parsing toward the end. Thank you. Hello everyone, welcome to my lecture. Word weighting, TF-IDF. The first correction to bag of words is the idea that some words are more important than others. In some cases, we know a priori which words to pay attention to, but more often we are faced with a corpus of documents and have to determine from it which words are worth counting in the word vector and what weight we should assign to them. The most common way to do this is term frequency inverse document frequency, TF-IDF. The intuition behind TF-IDF is that rarer words are more important. You calculate the word vector for a particular document by counting up all of its words frequencies as usual, but then you divide each count by the frequency of that word in the training corpus. This will dampen down the scores for common words, but balloon them for rare words that happen to occur frequently in this document. Generally, in a TF-IDF, you will only look at words that have some minimal frequency in the training corpus. If a word never occurs in the training corpus but shows up in a new document, then surely it shouldn't have infinite importance, and we don't want to give aberrantly high importance to a word that shows up only once. 5 occurrences in the corpus is a common minimum for the word to be counted. Even requiring just 2 will chop out a lot of noise such as typos. Endgames. Often we don't want to look just at individual words but phrases. The key term here is an n-gram, a sequence of n words that appear consecutively. A piece of text containing m words can be broken into a collection of m minus n plus n n-grams, as shown in the following figure. You can create a bag of words out of n-grams, run TF-IDF on them, or model them with a Markov chain, just as if they were normal words. The problem with n-grams is that there are so many potential ones but out there. Most n-grams that appear in a piece of text will occur only once, with the frequency decreasing the larger n is. The general approach here is to only look at n-grams that occur more than a certain number of times in the corpus. Stop words. Bag of words, TF-IDF and n-grams are fairly general processing techniques which can be applied to many other areas. Now let's move into some more NLP oriented extensions to bag of words. In most cases, this consists of a pre-processing step that canonicalizes the text, putting everything in a standardized format suitable for downstream processing by something such as TF-IDF. The simplest version is to remove what are called stop words. These are words such as the IT and that aren't really informative in and of themselves. They are critically important if you are trying to parse the structure of a sentence, but for bag of words they are just noise. There is no absolute definition of stop words. Frequently, they are found by taking the most common words in a corpus, then going through them by hand to determine which ones aren't really meaningful. In other cases, there is a list of them pre-built into an NLP library. Stop words become problematic when you are using n-grams. For example, the very informative phrase to be or not to be is likely to get stopped out entirely. Lemmatization and stemming. The other big approach is called lemmatization. The lemma for a word is the base word from which it is derived. Intuitively, if we are making a bag of words, then running, ran and runs should all count the same. In linguistic terms, they are all variations of the lemma run, and we would want to turn them all into run as a pre-processing step. Some form of lemmatization is extremely important in English, but it is critical in many other languages. I was surprised when I first learned that English is actually fairly tame when it comes to modifying our words. Languages such as Spanish, for example, have an arbitrary gender assigned to their nouns, and any adjective will be tweaked to reflect that gender of noun it is describing. Thank you. Hello everyone, welcome to my lecture, Probability. So far, this lecture has tacitly assumed that you understand basic probability, such as the notion of independence and what an average is. This lecture will go into more detail, giving you a little bit of theoretical background in the subject and an overview of the standard tools. In practice, data scientists only need a moderate amount of probability theory for most of their daily work, but that moderate amount is crucially important. Probability provides the theoretical basis for almost all of machine learning and most of analytics, and it is a critical mindset for data scientists to be able to adopt. Probability is often confused with statistics. The way I would break it down is to say that probability is a collection of techniques for describing the world using mathematical models that include randomness. In particular, probability focuses on what you can derive about the world, assuming that it is well described by one of these models. For example, if we assume a certain distribution of human heights, then how many people in a crowd can we expect to be over 5 feet tall? Statistics is more about working background. Given some real world data, what can we infer about the real world process that generate it? This lecture will attempt to build up the subject of probability in a very intuitive way. I will start off by showing two of the simplest, most intuitive and most important probability models. Using these as motivation, I will then zoom out and give a more formal treatment of probability concepts. Flipping coins. Bernoulli random variables. The simplest probabilistic model is just flipping a coin. Let's say that the probability of getting a head is p, and hence the probability of tails is 1 minus p. In probability terms, we would say that the flip of such a coin is a Bernoulli random variable, or Bernoulli RV. You might see it denoted as Bernoulli. The assignment of 0.7 to heads and 0.3 to tails is called the probability mass function for this particular random variable. It becomes convenient to describe the RV in terms of numbers rather than sides of a coin. The convention here is to say that heads equal to 1 and tails equal to 2. In many cases, there is some kind of payout associated with the different outcomes of the random variable. For example, I might give you $5 for every head and demand $2 from you for every tail. The average payout will be E equal to 0.7 into 5 plus 0.3 into minus 2 equal to 2.9. The right way to interpret this number is that if you flip the coin n times, where n is some very large number, you will make about 2.9 into n dollars. Throwing darts, uniform random variables. Bernoulli random variables are the simplest type of discrete random variable. The opposite is what are called continuous random variables. They can take on any value within a range of numbers. The simplest continuous random variable is the uniform random variable, sometimes called uniform bracket a into a dot b. A uniform a dot b will always be between the numbers a and b, but it is equally likely to be anywhere in that range. For discrete random variables, the probability mass function assigns a finite probability to every possible outcome. For continuous random variables, every exact outcome has probability 0, but certain range of outcomes are much more likely than others. We call this relative likelihood the probability density function. The PDF for a uniform distribution appears below. Similarly to probability mass functions, the constraints on a PDF f are that fx is never negative and the total area under the curve of f is equal to 1.0. Any function f that meets these criteria is a valid PDF. Related to the PDF is the cumulative distribution functions. Conventionally, if we use the lowercase f to denote the PDF, we use the uppercase f to denote the CDF. Fx is the probability that a random variable's value will be equal x. So fx is a non-decreasing function that goes to 0 as x approaches negative infinity and approaches 1.0 as x becomes large. In places where fx is large, fx will slope up sharply. In places where fx is 0, fx will be flat. The PDF tends to be a lot easier to think about and visualize. However, there are situations where it is easier to solve problems using the CDF. Thank you. Hello everyone, welcome to my lecture, The Uniform Distribution and Pseudo-Random Numbers. The uniform distribution is the most fundamental probability distribution to understand. It is the simplest one, but it is also the basis for building up many more complicated ones, both in mathematical theory and conceptual practice. For example, if you want to simulate a Bernoulli random variable b, then you can do it by simulating a random value u from a random distribution. If u less than p, then set b equal to heads, otherwise set b equal to tails. If you want to simulate the roll of a weighted dice, divide the range 0.0 1.0 up into 6 regions, the ith of which has size equal to the probability of the ith face. Then again draw a value u from a uniform distribution. Have the dice roll be the region of bracket 0.0.1.0 into which u fails. If you want to simulate an exponential random variable, draw u from a uniform, then take -1 times log u. In general, say you know the CDF fx of a random variable x. Say also that you are able to compute the inverse of fx to the power -1 u. Then fx to the power -1 u will be a sample of x if u is drawn from a uniform. For these regions, computational libraries that simulate random variables tend to start with sampling the uniform distribution as their most fundamental operations and build everything up from there. Now, technically, it is not possible to simulate random numbers with a computer. They are deterministic machines, capable only of following predetermined rules. There is no routine for flipping a coin, so the standard practice is instead to use pseudo-random numbers. The idea is this: you start with an arbitrary sequence of bytes The bits of that sequence are interpreted as the digits of a uniform random number expressed in binary out to a fixed number of decimal places. In some implementations, only part of the array is interpreted as a number. There is then a complicated mathematical function that mangles the byte array into a new byte array. The new byte array is technically a deterministic function of the old one, but in practice it bears no noticeable resemblance to the original array. Flipping a single byte in the original byte array could change bits anywhere in the output. The new array is treated as a new uniform variable and so on. The one great thing about pseudo-random numbers is that you can manually set the initial byte array at the start of a program. In this case, it is called the seed. If you do this, then the program becomes fully deterministic and you can reproduce it exactly between two runs. This means the following. If there is a bug in a randomized program that you only occurs sometimes, you can make it perfectly reproducible and figure out what's going on. If you need your analytics results to be exactly reproducible because somebody will scrutinize them, you can set the seed in your scripts. When you are writing tests, you can set the seed and make sure that the output is exactly what's expected. Oftentimes, you have two pieces of a code that you need to make sure work identically. The easiest way to do this is to make sure that they produce the same output given the same input. This becomes impossible if the code includes calls to random numbers, unless you set both of them to have the same random seed. Non-discrete, non-continuous random variables. Mathematically speaking, you can have random variables that are neither discrete nor continuous. For example, take the heights of trees that you have planted. At a given point in time, a certain fraction of them will not have sprouted and will have height 0. This is a finite probability match at that number. But of those trees that have sprouted, their heights can fall anywhere within a range. In practice, this is not a big deal. You are not dealing with abstract probability distributions, but finite datasets. A hybrid distribution would show up just as there being multiple identical numbers in the otherwise continuous valued data. Calculating the mean, average, median, or other metrics of interest would still be exactly the same procedure. Thank you. Hello everyone, welcome to my lecture. Big data. There is a lot of overlap between the terms data science and big data. In practice, there is a close relationship between them, but rarely they mean separate things. Big data refers to several trends in data storage and processing, which have posed new challenges, provided new opportunities, and demanded new solutions. Often these big data problems required a level of software engineering expertise that normal statisticians and data analysts weren't able to handle. It also posed a lot of difficult, ill-posed questions such as how best to segment users based on row-click stream data. This demand is what turned data scientists into a new distinct job title, but modern data scientists tackle problems of any scale and only use big data technologies when they are the right tool for the job. Big data is also an area where low-level software engineering concerns become especially important for data scientists. It's always important that they think hard about the logic of their code, but performance in concerns are a strictly secondary concern. In big data though, it's easy to accidentally add several hours to your code's runtime, or even have the code fail several hours due to a memory error, if you do not keep an eye on what's going on inside the computer. What is a big data? Big data, as the term is used today, is a bit of a misnomer. Massive data sets have been around for a long time and nobody gave them a special name. Even today, the largest datasets around are generally well outside of the big data sphere. They are generated from scientific experiments, especially particle accelerators, and processed on custom made architectures of software and hardware. Instead, big data refers to several related trends in data sets and to the technologies for processing them. Big data requires a few words of question. The first is that you should be hesitant about using big data tools. They are all the rage these days, so many people are jumping on the bandwagon blindly. But big data tools are almost always slower, harder to set up, and more finicky than their traditional counterparts. This is partly because they are new technologies that haven't matured yet, but it's also inherent to the problems they are solving. They need to be so flexible to deal with unstructured data, and they need to run on a cluster of computers instead of a standalone machine. So if your data sets will always be small enough to process with a single machine, or you only need operations that are supported by SQL, you should consider doing that instead. Hadoop, the final system and the processor. The modern field of big data largely started when Google published its seminal paper on MapReduce, a cluster computing framework it had created to process massive amounts of web data. After reading the paper, an engineer named Doug Carting decided to write a free open source implementation of the same idea. Google's MR was written in C++, but he decided to do it in Java. Carting named this new implementation Hadoop after his daughter's stuffed elephant. Hadoop caught on like wildfire and quickly became almost synonymous with big data. Many additional tools were developed that ran on Hadoop clusters or that made it easier to write MR jobs for Hadoop. There are two parts to Hadoop. The first is the Hadoop distributed file system. It allows you to store data on a cluster of computers without worrying about what data is on which node. Instead, you refer to location in HDFS just as you would for files in a normal directory system. Under the hood, HDFS takes care of what data is stored on which node, keeping multiple copies of the data in case some node fails and other boilerplate. The second part of the Hadoop is the actual MR framework, which reads in data from HDFS, processes it in parallel, and writes its output to HDFS. Thank you. Hello everyone, welcome to my lecture. Using HDFS, data can be accessed and manipulated in HDFS through a command line interface, which is based on the standard base shell. These commands are pretty Spartan, but they do everything you need to. One of the first things you will notice as you work with HDFS is that many of the files have names such as part M00000. This is a near universal convention among data processing tools in Hadoop. The directory containing those files will be the output of a single job that was distributed across multiple nodes in the cluster. The files themselves will be the outputs of different parts of the job that were going on in parallel, and they are stored on the cluster node that generated them. Occasionally, it's more convenient to just use HDFS rather than the big data analysis tools themselves. This is because most of these standard tools involve tremendous overhead, but the HDFS commands are very fast. When used in conjunction with the normal base shell, you can often get an edge in performance and convenience over the main tools. Example, PySpark script. PySpark is the most popular way for Python users to work with big data. It operates as a Python shell, but it has a library called PySpark, which lets you plug into the Spark computational framework and parallelize your computations across a cluster. The code reads similarly to normal Python, except that there is a Spark context object, whose methods let you access the Spark framework. If Spark is installed on your computer and you are in the Spark home directory, you can run this script on the cluster with the following command: bin/spark submit master yarn client myfile.py. Alternatively, you can run the same computation on just a single machine with the following command: bin/spark submit master local myfile.py. Spark overview. Spark is the leading big data processing technology these days in the Hadoop ecosystem, having largely replaced traditional Hadoop MR. It is usually more efficient, especially if you are chaining several operations together, and it's tremendously easier to use. From a user's perspective, Spark is just a library that you import when you are using either Python or Scala. Spark is written in Scala and runs faster when you call it from Scala, but this lecture will introduce the Python API, which is called PySpark. The example script at the beginning of this lecture was PySpark. The Spark API itself is almost identical between the Scala version and the Python version. Spark operations. This section will give you a rundown of the main methods that you will call on the Spark context objects and on RDDS. Together, these methods are everything you will do in a PySpark script that isn't pure Python. Configuring Spark. Clusters are finicky things. You need to make sure that every node has the data it needs, the file it relies on, no node gets overloaded, and so on. You need to make sure that you are using the right amount of parallelism, because it's easy to make your code slower by having it be too parallel. Finally, multiple people usually share a cluster, so the stakes are much higher if you hog resources or crash it. All of this means that you need to have an eye toward how your job is configured. Spark tips and gotchas. Here are a few parting tips for using Spark, which I have learned from experience. Number 1. RDDS of dictionaries make both code and data much more understandable. If you are working with CSV data, always convert it to dictionaries as your first step. Yeah, it takes up more space because every dictionary has copies of the keys, but it's worth it. 2. Store things in pickle files rather than in text files if you are likely to operate on them later. It's just so much more convenient. 3. Use take while debugging your scripts to see what format your data is in. 4. Running count on a RDD is a great way to force it to be created, which will bring any runtime errors to the surface sooner rather than later. 5. Do most of your basic debugging in local mode rather than in distributed mode, since it goes much faster if your dataset is small enough. Plus, you reduce the chances that something will fail because of bad cluster configuration. 6. If things work fine in local mode but you are getting weird errors in distributed mode, make sure that you are shaping the necessary files across the cluster. Now that we have seen PySpark in action, let's step back and consider some what's going on here in the abstract. Thank you.